Yeah, so it's essentially what is INLA. It's essentially doing approximate Bayesian inference for a very specific class of models, and this is the class what's called latent Gaussian models, or it is called the latent Gaussian models. The point is that this very, very simplistic case of model is super popular. We're using it much more than we think. And many models you use is exactly can be seen as a latent Gaussian model. And thereby this kind of more general view to do the inference for this class of models is very, very useful. And why do we use that? If you have a latent Gaussian model, you think you have a Gaussian. There is so much kind of structure here that we can take advantage also computationally. So we can do it very, very quick. And it turns out because of this, there is so much kind of structure here that is known. We can even do that. My claim, we could do it better than MCMC. Not uniformly. You can always find counterexample, but normally for a kind of given fixed running time, we can do way, way, way better, essentially. And this is another kind of strategy. I'm totally fine not be able to do all models. It's like people, you cannot do this model in INLA. And that's totally fine, I don't care. You know, it's all about, if we can do a subclass of model better is really beneficial. And then Stan that you learn about, they can do the other things. And I think this kind of class of latent Gaussian model, this is the most important construct we have because it contains essentially so much of really what we're doing. First, a little kind of background about the project. I was looking, there is a specific website, rinla.org. Look like this. It's very kind of old-fashioned. We should kind of switch it to the new Google site look. That would be much better. There are, in fact, books about this kind of thing. So it's not, there is some documentation here. This was the first one about space-time models with INLA. There is this kind of, from the Highland Statistics group, so they're more like professional consultants, and they go around, especially in ecology, biology, environment, and give courses. They have all courses on this. There is a new one, Bayesian regression modeling with INLA. There is a part 2 from this kind of consulting groups. And there is also a new one here from our team about the SPD models, doing kind of spatial models in INLA that will come out early next year. This book also is a free version on GitHub. So if you go to the INLA page, you can go to books, you find the address. So this book would also exist like a free version, and you can also buy it in print. I just want to show you, just to show that people kind of using this in various kind of areas. I just looked up what happened the last the 2 weeks, just to see what kind of applications are there that have been in print the last 2 weeks, that kind of using this kind of software extensively for doing the analysis. So here it is. Here is one. This is paleoclimate reconstructions. You have this Chagas disease mortality in Brazil. It's another one, HIV infection in Kenya. The funny thing, you end up with kind of journals you have never heard about, sociobiology, I don't know what it is, but they're doing kind of wood ants into plantation, yes. If you go into details, sometimes a supplementary material, you find it there. There is this huge project, Malaria Atlas. So our interface to global, this kind of malaria data. Journal of Ecology, Ladeprans. Yeah, it's wind speed forecasting, space-time dynamics, risk factor, human, something in Brazil, environmetrics. There is a lot of things, and it kind of, you see, this is not kind of mainstream statistics journals, and this is the most one kind of very characteristic. It's like you end up, although this is kind of known, there are many kind of journals that is never heard about before, and this is like a recent thesis from Trinity College. If you look to activity, there are some kind of discussion groups. You find it on the R-INLAB webpage. And how many users do we have? I don't know. What we can do, we can kind of track traffic to this site. And then the kind of the number of users will essentially be proportional to this, you know. So we are about monthly, let's say about 3,000, on average 3,000 users visits a month. I don't know, so it's proportional to 3,000, okay, a month. I think we are present in most countries. If I go to, if I check where the kind of they come from, it's not very clear. There are some countries in Africa where we kind of empty, and also I think go here North Korea. We are not in North Korea. So otherwise we are in Greenland. Greenland is empty. Otherwise I think we are mostly present. Everything here is kind of open source. It's kind of free source. All the code is available out there. You can go to the code repository at Bitbucket. No, at yes, Bitbucket. And you can look at all the commits, everything is open, everything is there. So who is involved? The code is essentially written by me and Finn Lindgren. He's now in Edinburgh. There are many other people that are directly involved. I don't know. It's becoming is by no means compared to the efforts in STAN, but there is a lot of people involved directly, indirectly in this kind of loose project. Okay. So what is it we do? And for me, it was the starting point that even though we had MCMC, I don't consider the statistical Bayesian computing for solved. Even though we thought this was going to be solved in 20 years at a time, if you go 20 years at a time, 25 years at a time. Earlier, when I started, then I thought in 20 years' time everything would be solved. But this is not the case. And I think one of the reasons is that essentially you had the development in a little bit, you also have MCMC, you have all this development in computing, but you also have the development in models. Okay, so as long as the computing becomes more, you can do more. You want to do more. You not only want to do the models you did faster, you want to expand it. So we are always on this edge of having models that are too slow. Of course, if you want to do this Bayesian modeling, you have to do the Bayesian computing, and we have JAGs, and you hear a lot about STAN based on MCMC, and they are quite generic. I'm a big supporter of the STAN project. It's a wonderful project, but still, it's for many of these kind of models that we discussed here, it's still slow. Okay. Or you might phrase it as still slower than you would like them to be, okay? So if we can kind of solve one class of models better, which should it be? And you have all these kind of models based on generalized linear models, generalized additive models, and generalized additive mixed models, and you all put these acronyms together and you get a new one, and they are all the same. essentially the same thing. And these are essentially the most important class of models that we have. Of course, you can find something else. All this kind of issue about mixture models, they are also important, but the models that people are using in practice is very much in this class of models. And also here, there isn't kind of good enough MCMC solution around. You can do it, but it's still kind of slow. And as soon as if you're used to kind of getting results in terms of very quickly, in terms of, we're talking about seconds, and sitting there waiting for a few minutes, it's long. And there are also many of these kind of approaches that doesn't really scale well. Scale well in terms of not necessarily the number of data, but the size of the model. And now we're thinking about that a model size of some 1,000 is small, 10,000 is medium, and 100,000 up to million is getting larger. Okay, so this kind of scale we're talking about. So what is this kind of all these generalized linear models and additive models and all these kind of things? It's nothing else than a linear predictor. And a linear predictor that is kind of, you construct it by adding terms. The terms you kind of add is like, it's the same thing. It's like an intercept. There are what's called fixed effects. We call it fixed effects just to not mix up the terminology. But there are also kind of random effects, which is again just something random, and you add linear combination of that. You know, historically, random effects is just there to kind of tweak the covariant structure, but nowadays we also use it to kind of tweak the mean structure as well. Okay, we're thinking about spline, we're thinking about time series models, we're thinking about measurement error models. All of this is part of some kind of random effect. Okay, and the random effect is simply, here is just written just IID, this is a classic thing, but you can think of this as some kind of Gaussian process. Okay. And then, so you're kind of building up this kind of linear predictor, and you think that these coefficients for the fixed effect, if they are Gaussian, you're adding up random effect that is also Gaussian. Linear combination of Gaussians is still Gaussian, so you end up with a linear predictor that this has some kind of Gaussian structure. Then we add observations. It could be some parameters here, and they are very much conditional independent. Okay, so essentially you have one data point only depending on one linear predictor. So linear predictor is kind of the linear predictor for that data point. Here is just some examples. This is just a time series of counts. This is like the raining in Tokyo for 2 consecutive years. So it is 0, 1, or 2. So this is just over years. So the data is a sequence of 0, 1s, and 2s, and essentially binomial. And you can binomial data, and you can think of there is an underlying trend behind here. So like the probability for rain is controlled by this linear predictor. It's a function of time, and this time is like on a yearly basis, and it's the same every year. So it's a kind of model on a circle. Okay, and we can think of building up a linear predictor. You can have some kind of an intercept. You can have covariates. You can have like a spline models on a circle. You can add another kind of random effect. You can build this up, but all these terms is kind of is Gaussian. And all this kind of, you make the sum, this also kind of Gaussian, and you have a linear predictor that's also Gaussian. So you have this very kind of specific structure, Gaussian structure. And you can kind of rewrite this model very, very simple. You have some parameters, theta, and I say parameters, or hyperparameters. It's like, think of them as the non-Gaussian component, variances or precision, correlation. They could be over-dispersion, anything that's up there that is kind of non-Gaussian. And then there is some Gaussian component. Here is written with the covariance matrix. And inside this component, there is this linear predictor. Okay? So it means that some of these components here are observed, and you have this conditional independence in the observations. So you see here, this structure is embarrassing simple. But at the same time, it has so much structure. It has the structure because the whole is latent process that kind of is the important thing, is Gaussian. And this is just a variance parameter over dispersion. They are few. There's only a handful of them. And this is the kind of typical structure. These parameters are on top is very few because they relate to the number of components in the model. Whereas dimension of this latent field, this is related to the number of observations in the model, the size of the model. Okay? So what you have here is that instead of, this is the covariance matrix, but if we instead of the covariance look at the inverse, which is called the precision, then we'll see that this has, again, kind of much better properties. This is just a plot of a simple model in this case. So what you see in the red is a non-zero terms. So you see this kind of matrix is essentially empty, has order n, non-zeros, and it's n by n matrix. Okay. So if you do the reordering, you do the factorization. So this is a factorization of this kind of matrix, and you see this essentially can be done linear in time. So we can do this kind of time series models, kind of linear in time. And this is by no means kind of surprising because most of the time series algorithm is linear in time, but these kind of algorithms really generalize to kind of more general graphs. Here's another one, just to do a spatial one, the seas mapping. This is like a classic model, it's almost too boring. So in each of these kind of counties, region, you have like a count, like a Poisson count of something, number of occurrences of some disease. And you kind of build up this model by having a linear predictor, which essentially like you want to do some kind of smoothing, some kind of random effect, and some kind of non-parametric smooth effect of some other covariates. So the smoothing you want to kind of impose is that saying that what happened in one region is similar to what happened in the region nearby. It's very kind of simple structure. If you do that, you end up with a precision matrix for the whole Gaussian part of the model that looks like this. So what you see here, this is the spatial part, and this part here is like an effect of a spline effect of a covariate. Okay? But you see that it's essentially, this matrix is essentially zero. If you do the reordering, you do factorization, so this is the factorization of this matrix. So this is the kind of backbone for doing the computations by never essentially touch or construct covariance matrices. We always work with inverse. And the inverse has this very, very, very sparse structure. And this is kind of the main driver in all the kind of computations. And also here you can rewrite it into this form. Again, it's the same form that we had previously. Number of parameters here, theta is dimension 3. And then you have this Gaussian component with a kind of precision matrix, in fact, square root of that has this form. And then you have some observations, so only a part of this matrix. Essentially what happened up here, these are observations. So you see here, so even this model can be interpreted in the same structure. And this is the thing, if we can kind of do the inference of this model that apparently doesn't look like anything, we can take all these kind of different models, we can rewrite them into this form, do the inference, and take the result back. So this is like the generic representation of this class of models. And this is what we call, or what is called, a latent Gaussian model. This is our definition of this. You find this everywhere. Volatility model, all these generalized models, measurement error models is also there, or spline smoothing. A lot of these smoothing things can be cast in this form. Space varying regression, disease mapping, these log Gaussian Cox process models. This is like a big hit. It's also have this kind of form. Model-based kind of geostatistics, we need some new tools to do this. Space, when you go to models in space and time, it's like there is more restricted what you can do. There is even more structure, so then it's basically a Gaussian model. Survival analysis, and all these kind of models that combine joint survival analysis and longitudinal data, they're also kind of trivial in this setting. Okay. So what is the key thing? The key thing is that we have to work with this, what's called the precision matrix instead of the covariance. If you think of, we want to do models of size 10,000, 100,000, million, or even a few millions we can do now, then even if you could do the covariance, you cannot even store it. Okay? So this doesn't work. This is like a dead end to think about covariance. And to think about the precision matrix, this has this main advantage that it's a natural tool when we build up models through conditioning or a hierarchical model. If you have one, we have an intercept and we add the covariate and we add this and we add this and this. The natural language is precision matrices. Okay, we'll see how this is. And certainly this is my favorite slide. This is like deep down there is a detail that without that nothing would work. Okay? So this is why, essentially why something like this can work. Okay? So this is an example how precision matrix play well with these kind of hierarchical models. Okay? So think of, we have some x is some vector, it's normal with some precision matrix qx, and then conditioned on x, we just place x in the mean here, and then we have another layer. And then you can, of course, kind of continue this. And you can put in linear combination matrices everywhere, it's all the same. The thing is that the joint precision matrix for x and y has this very, very simple form. Okay? So you start with a precision matrix for x, and then you add the next layer, so you just add the qi. And then if you have a third layer, you just add the q set, and so on. So this, you can kind of construct the precision matrix. There is no matrix multiplication, there is no inverse. You can just take one, you can add another one, add another one, add another one. It also means that if I change a parameter, like a variance parameter, I need to recompute the precision matrix. You see there is hardly anything to compute. It's just one element in the sum that changes. Okay? And this is so important. If you try to do the same thing with the covariance matrix, what is joint covariance of x and y is horrible. If you then have to recompute it every time you change some kind of overall parameter, computationally you're simply dead. So it doesn't work. Of course, all these kind of the parts of this is kind of course already known. This is the the Kalman filter, the Kalman recursion, the Kalman update, the Kalman smoothing, which is like the kind of a special case what happens if you work with a time series model. Okay, and essentially these kind of things in what you get in the Kalman update. So if you have a new observation at the next time point, you simply add another term here, and you can kind of update the Cholesky factorization. This is Kalman update. Okay. So what do we really need to do all this? We need to factorize matrices. So it's a symmetric positive definite matrix. You have a Cholesky factorization. This is the main computational tool. Based on that, you can solve linear equations. We also need the smoothing term in terms of we need to compute the diagonal of the inverse of this matrix. And this we can also do very, very efficient. Okay. To turn out, you can make use of this kind of sparsity in these matrices to kind of reduce the computational cost from n cubed, which is general, into if you have long and thin models, you're basically linear. If you, in space, you're like n3/2, which is square root of the time. And space-time, we end up with essentially n squared. So this is how far, essentially, you can kind of push these kind of algorithms. And the kind of the reference is like n cubed. And even if you can do n cubed algorithms up to, for dense matrices up to some size, at some point, the memory is going to kill you, you know. Also, the kind of the storage cost is also very beneficial. It's essentially go like n log n. Okay, so it's very kind of compact storage, which also makes everything much faster. It turns out that if we really want sparsity in these matrices, all these kind of building blocks we put in also need to be sparse. You cannot put in a kind of a model component with a dense precision matrix and just hope that it will turn out to be sparse. No, you have to kind of start with only kind of model component that has a sparse precision matrix, and from these kind of build on. So there is a slight restriction on what models you can use. And these kind of Gaussians with a sparse matrix, they are called Gauss-Markov random fields. And they are kind of useful in itself. You can really, they really play well, and you can really do very fast computation on them. So they are also very useful in other settings as well. Okay. So in inline, there are kind of three main ingredients. You have these Gauss-Markov random fields, these kind of small model components that has a sparse precision matrix. You have this formulation of the latent Gaussian model, this kind of very, very simplistic model class. And you mix this with the old concept of Laplace approximations in a very hierarchical way. And it's like, the amazing thing, if you go through the math, it's almost like it's too good to be true. So everything you hope for turned out to be true. So there are these things. Oh, yeah, we can do this very, very quick. It's very accurate. It's a relative error. Has good scaling properties because the scaling is done by these sparse matrix algorithms. Okay. And other properties as well. Just to show you one example, this is a kind of leukemia survival data. It's part of northwest England, I think. And here we kind of have occurrences of this leukemia. So this is like an example from more than 15 years ago. Okay, and at that time, of course, this was in the around 2000. Maybe development was in late 1990s. So at that time, they the PhD student that did it said they were running this for weeks. You know, at that time, of course, this was the thing, and you kind of formulate this as a Cox proportional hazard model, and we can do that by using like a Poisson regression reformulation. So you have a log baseline, you have some function of the covariates, you have a kind of regional effect of location, you have fixed effects, and so on. So it's like a kind of classical model. Not a classical, not a very difficult one, but at that time, this was a challenge. And you can do this is a code, and you get result. So the results you get from this kind of software is simply the computed or the approximated marginal distributions. Okay, and from the marginal distributions, you can derive statistics like the mean, variance, quantiles, all these kind of other properties. Okay, so the output is marginal distributions. You have effect of covariates and all this kind of result. This is the log baseline hazard. The important thing is here. So now I can run it on my simple laptop in like roughly 2 seconds. I can do all the math. But just to show you that this, here, this is not a large model. So we're working with matrices of dimension roughly 2,400. So we have, if you count the kind of numerics behind it, we have to factorize this matrix about 450 times. We have to solve about 3,000 linear systems. And we have to partially invert the cube, compute the kind of the inverse of cube, but not all of them, only the elements we need, about 28 times. So you see that there is a lot of numerics going behind it. This is not kind of simulation. This is like a deterministic algorithm. So unless all these kind of terms goes quickly, there is no way to do this, you know. And this is a small model. Okay. So what is it all about? So why do we have this kind of sparsity? And this is related to the concept of conditional independence. So Gaussians that had a sparse precision matrix is called a Gauss-Markov random field. It's nothing else than a Gaussian vector that has additional Markov properties. It's kind of the parallel development that you have elements that are independent. So covariants work with independence, precision matrices work with conditional independence. Okay. So if you know some of these, so xi and xj are conditionally independent given the rest, then it turns out that you get this kind of sparsity. So if you know which one that are conditionally independent, you cannot really represent that in the covariance matrix easily, but you can do that very easily in the precision matrix. And the result is very simple. If you have conditional independence, you have a 0 in the precision matrix. So this is the analog to the case where you have a 0 in the covariance for independence. But independence is a too strong kind of concept. Conditional independence is much, much more useful. Okay. So based on this concept of conditional independence, you have useful properties, and the most useful one is kind of the global Markov property. So if you kind of represent the conditional independence by a graph, so if it's not conditional independent, two nodes are connected. Okay, this is called a conditional independence graph. If you do that, then you have this kind of nice interpretation of conditional independence properties on the graph. And the useful thing is that if you have two nodes that separates a subset of the other nodes, like the black and the shaded ones, if there is no path from one set to the other one without going through this separating set, you have conditional independence. And this is the really useful thing. So when you have these sets of conditional independence, you essentially mean that in this precision matrix, you have this big chunk of the matrix that is zero. And zeros in matrices are a good thing if you want to compute with them, because if you have a lot of zeros, maybe you can figure out something else is also zero, and if you know it's zero, you don't need to compute it because it's zero. And that's the only idea. Okay. So the simplest kind of non-trivial example of this kind of model is the autoregressive order 1 model, this simple time series model. So you have a graph like this, and if you use conditional independence, if you fix x3, then x1 and x5 is conditionally independent. Okay? So simply that if x3 is that is fixed, there is no connection between x1 and x5. Which means that there is a lot of conditional independence. If you work out the precision matrix, it's just a tridiagonal matrix. Of course, and this is tridiagonal. First order, if you go to second order, there will be five diagonal matrix. Okay. That's why these models are so fast to compute with. So the main thing to do the computation is like the Cholesky factorization. So if you have a symmetric positive matrix, it's simply like a kind of a square root of that matrix. So L is a low triangular matrix. And solving equations, AX is B if this symmetric positive definite. It's simply first you factorize the matrix and then use that to kind of solve the matrix. Solve the linear systems. So how is this done? This is if you factorize the matrix, you have a low triangular matrix. If you want to solve AX is B, you first solve the forward substitution, the forward loop. So you solve LV is B, and then you take the solution and you solve it the other way. So you do the forward, and then you do the backward. And this kind of forward-backward idea, and this we have heard before, okay? So all this kind of forward-backward sampling, filtering thing, this is essentially nothing else than solving a linear system. Okay. And this is also what we do if we want to sample from a Gaussian with this kind of structure. We'll simply factorize the precision matrix and solve a linear system. So you have to do the solve going backwards. So you factorize the matrix, and then essentially you have to sample the process backwards to have this backward substitution. So you see that you can equally well do the sampling in using precision matrix instead of looking up to doing the Cholesky factorization of the covariance, and then it's just a forward sample. Okay. And here, if we have this, you see that if we have the factorization, you also have the determinant of Q, because it's just a determinant of a lower triangular matrix square. It's just the product of the diagonal terms. Okay, so the normalizing constant is also available as soon as you do this factorization. Okay, yeah, this is not so. The funny thing is to look at how these guys in doing the sparse matrix algorithms, how that work. And it's possible to kind of explain everything from a statistical point of view. So the main thing is the Cholesky factorization, and we can kind of explain why this is working and how it's working and what make it work by only using kind of concept of conditional independence. So the concept is why you can factorize this faster is not that this matrix is tridiagonal, and you look up in a book and you find an algorithm for tridiagonal matrices, and it's super quick, it's linear, and you put it there. But why this works? Okay, this is the important thing, and how we can take advantage of this, and this concept of permutation. This is so important. Okay. When it comes to Cholesky factorization, so we have Q is L transpose. L is a lower triangle matrix. There is no algorithm for Cholesky factorization real. There is no trick. If you spell out, if you write it out, you can see that you can directly solve L. You do one, and based on this, you can do the rest of this column, and then you go to the next one. So there is, to compute this is like a no-brainer. There is no clever algorithm behind it. So if we know that some of these terms are zero, it's super easy technically to kind of take advantage of this by simply not computing them if we know they are zero. Okay? So this factorization is kind of direct. You just say Q is a lower triangular transpose, the same thing, write out the element and start in one end, and you can directly write down what the solutions are. Okay. The point is that if we're going to understand how we can kind of factorize these matrices better or faster, how we can take advantage of these kind of zeros, we need to kind of have an understanding what the Cholesky triangle of this precision matrix is. And if we have an interpretation of that, we can kind of move forward. So the interpretation really starts by saying that L transpose X, if Z is just noise, normal noise, this is a sample from the correct distribution. So it's like this backward step. So if we just kind of spell out the terms and start from the last one, we have that the last element, xn, is simply 1 divided by ln and zn. This is standard normal. So it means that the marginal distribution for xn, the variance is 1 over ln squared. Okay? And then condition on xn, so we take this value and move back here. This is like solving the next term. You see that this enters in, this is a constant now, and this enters in the mean, and the only random term is this. And this, you have this scaling that come from the diagonals, mean that the conditional variance, condition on those with a higher index, is related to the diagonal terms, and the off-diagonal terms is simply related to the conditional mean. Okay, so if you kind of write this up, you have that this Cholesky triangle of the precision matrix gives this kind of a time series going backwards. So the expected value of xi, condition on those with a higher index, is simply a linear combination of xj, and the precision is this diagonal term squared. Okay, so this gives interpretation, and the key observation now is simply to see that if I fix one x at j here, if you think that xi and xj would be conditionally independent, condition on those with a higher index, then this term here must be 0. Okay? So conditional independence, not in terms of the whole joint distribution, but the distribution for xi and those with a higher index, just a subset of the distribution. If you have conditional independence there, then this term here will be 0. And this is the kind of the key concept. So if you think of, so f is like the future, so the future of I except j. So it means that all indexes higher than I, but not j. So it's like I plus 1 up to n, but j excluded. If you have conditional independence here, then this term must be 0. Okay? And this is the kind of the main result. If we can kind of determine conditional independence, not in the whole distribution, but in this from xi and upwards, if you have conditional independence there, then you have a 0 in the Cholesky factorization. And the idea here is, of course, if you know that this is 0, you don't need to compute it. And this is how this works. So we need some kind of way to kind of verify conditional independence, not in the whole distribution, but in the marginal distribution from xi up to xn. Okay? It turns out that this is essentially impossible to do in a quick way. The easiest way to do this is to compute L and check if this is 0. And then it doesn't help, you know. So we need something that is weaker than this, that if this is true, then this imply, and we accept that we cannot cover all the cases. And then we're back to this concept of global Markov property. If you have a set that separates two orders, then you have conditional independence. Okay? The good thing here, and this is like this is a property of the matrix, the numerical values of the matrix itself. What if we go to a global Markov property? This is a property of the graph. So it's much, much weaker. So we don't need to know the numerical values to do this. Okay? So if you've done it once and you have the same structure, you have the same result. Okay? So if you have this set that separates, then you have conditional independence. So it's all about finding a separating subset in this graph. So if the future separates I and j, then you have conditional independence, and then this element is 0. Okay? And this is the main result. So if the future separates I and j, then you have 0. And of course, two neighbors cannot be separated because they are neighbors. And that's it. This is the idea. And then you figure out which one that is 0, and if you go back to the Cholesky factorization, which is a direct algorithm, you just compute term by term, you simply skip this term that you know is 0. That's the overall concept. To do that in practice, that's something else. But the overall idea is as simple as this. So this is the simplest non-trivial case, some of you have seen it before, but this is the simpler case. So here is a 4x4 matrix. This is the graph. So 1 connect with 2, 2 connect with 4, 4 with 3, 3 with 1. So you have this kind of model on a circle. So you have a non-zero term between 1 and 2, 2 and 4, 3 and 4, and 3 and 1. So the matrix looks like this, and the empty spaces are zeros. Okay? So if you want to kind of factorize this matrix, we know that if we have neighbors, then you have no separation. So it essentially means that the Cholesky triangle of this factor kind of inherit the non-zero terms in Q. But these two terms with a question mark, then it's a question if this is 0 or non-zero. Okay. So if you look at one term, this term 1 and 4, so essentially we take 1 and 4, and then we condition on the future of 1 except 4, so this will be 2 and 3. So essentially, is 1 and 4 separated if we by 2 and 3? And you see it's kind of separated. If you fix 2 and 3, there is no connection between 1 and 4. So that means that this term here is always 0. And if we take this term, this is 3, 2. So in 3 and 2, if you take the future and 3 and 2 is 4. So if you condition on 4, you see that 3 and 2 are connected with 1. Okay? So it means that this term is in general not 0. So it means that the savings in this case is kind of minor. We don't have to compute L for 1 because it's always 0. In general, the savings are enormous, and most of the terms in L would turn out to be 0. Okay. So if you apply this kind of idea on this autoregressive order 1 example, you will see that you have a tridiagonal matrix, and then you have this L inherent the non-zero pattern, and then the question is all the rest. So this lower triangle, you have to check it, and if you check it, you find out that they all turn out to be conditionally independent, given the future. So there is no extra terms. So like here, you inherit the non-zero pattern from Q, but you have to do this additional point. For these autoregressive models, there is no additional points. So they are kind of optimal in that sense. Okay? So you see that it's like this term, so you get these linear algorithms. Of course, if you have a higher order time series, you get a higher, the width of the band is simply the order of the process. Okay. And based on this, and then you see that if you go back to the Cholesky factorization where you have loops going from the diagonal down to the column, it's super easy to take advantage of this. You know, you just let the loops go from the diagonal to the bandwidth, plus the bandwidth. So it's just working within the band, you know. And this was certainly one of the earliest ideas about sparse matrices, is that we can easily deal with matrices that are banded, and then the question if we can kind of, if you can kind of fake it. You can take any sparse pattern or some sparse pattern and turn it into something that looks like a band matrix. Okay. And then there is this concept of reordering. You don't need to take the matrix as it is. You can play around with the indexes. The indexes are not kind of given. If you can permute the indexes. You can do the factorization in the permuted world. You can permute the right-hand side, you get a permuted solution, you can do the inverse permutation to get the real solution back. Okay? So it's just, you map it into some other indexing. And this is the whole idea, and this is super duper important. So if you have this kind of spatial model that we had before, this correspond to this, so this is the kind of the corresponding graph. So what happened in one kind of region depends on what happened in the neighbor region, and you get the graph like this. So a way to kind of emulate a band matrix in this case, that you start with from one corner, like this, you start to count 1, 2, 3, 4, and up to here, and then you go back. You do the next one. So this is like a column-wise ordering or row-wise ordering of some kind of matrix. If you do that, that shows the kind of the indexes you will have. And then you can kind of convert this kind of matrix on the left, which is the matrix on the original indexing, to a kind of a band matrix on the right. Okay? And then you see that you can, this is like a band matrix, and then you can apply this kind of band matrix algorithm to this. So this runs way, way better. So you see the effect of simply doing the reordering. And this is like a major kind of technique in this with sparse matrices, because the cost is not invariant for this reordering. It turned out that we can do way, way better, because the the size of this bandwidth is essentially the length of the separating subset. And in this case, if there are n regions, this size will be order square root of n. And the cost for this band algorithm is n the bandwidth square. So n square root of n square. So this will be n square cost. It turned out that we can do square root of n better by doing something else. And this is this idea about divide and conquer. So this is the main idea. So if we have this kind of graph, so one, and then my way of thinking is that this is the intercept, and these are just random effects that we add to the intercept. And this is a very typical kind of structure we have for statistical models. We have nodes. We have a bunch of nodes that is essentially neighbor to anything, mostly anyone. And these are the intercept, the fixed effects, and so on. So we have this kind of setting very, very often. So if I have this kind of matrix, this is the precision matrix, and this turned out to be the Cholesky factorization. Because if I look to, if 3 and 4 are separated by the future, and the future is 5 and 6. You see they all connect through 1. So it turned out there is nothing to be saved by looking at the matrix of this type. So if you do the factorization, it turned out to be a dense matrix. So there is no saving because of the sparsity. Okay? And then we do this, simply swap 6 and 1. And we can ask the same, with 3 and 4 conditional those with higher rings, 5 and 6. And you see that as soon as you condition on 6, everything is conditionally independent. So if we do this form of the matrix instead, there is no what's called fill-ins. So this is, in this case, with 1 here and 6, just flipping these two, we're going from the worst case to the best case. Okay? So the whole idea is to have nodes that have many neighbors. You give them a high index. So you factorize them first. So if you do then the conditioning, you get this kind of separation. And of course, if you can take a set and divide it in a subset, you find a separating set that simply divides it. You apply this idea recursively. And it turned out then, in that case, you can get the factorization square root of n faster. It's n square root of n. And you only have like log n fill-ins, extra term you need to do for each row. And this is the optimal thing you can do. So in this case, you can kind of think, the first thing you'd have this is the first separating subset. It's divided into the southwest and northeast. And then you take each of them again and separate. And then at some point, this kind of algorithm just stops because the matrix is too small. It doesn't give you anything to continue. So then you end up with kind of reordered precision matrix like this. So this is the reordering. If you go back to the original form, you have this also on the left. So we have this algorithm that takes from the matrix on the left to this form, and then you have this factorization. And then you see also that this is like the basic idea for doing this in parallel. As soon as you have computed this term, the problem separates into two independent problems. And then you continue. So this is the kind of basic for doing this in parallel. Okay, so this is a divide and conquer idea. Okay, so these are the main ideas, and the question is, how do we use it? We just use existing software, because a lot of these things are notoriously complicated. People spend years. There are conferences on this. This is not yet done. This is a notoriously complicated matter. Okay. And in R, there is a recommended matrix that's already there in installation. It's called matrix. And there are different ways you can store sparse matrices. How you can store it as soon as you store it in one of these packages will normally be taken advantage of when you're doing this kind of factorization. And this reordering thing is like this is happening in the background. You don't really see it. Okay. Okay. Okay, let me quickly just show you how we can do the marginal variance, or how we can do the smoothing thing. The margin variance. And just recently, you can find this in, if you go to the default package in MATLAB, which is based on a library called Cholmod, it has this kind of a sparse inverse function. Otherwise, most other kind of large scales packages for sparse matrices don't have this kind of built in, because those who do use this kind of matrix to solve essentially finite element methods, they don't need this, you know, so it's not implemented, but you can do it. So this is like a result from 1973, and they applied this. They approached this by rewriting Q to this kind of form, this V as a low triangle matrix, and they derive a matrix identity. And if you stare at this, you can find out you can do that. So that was the idea. And this is a copy from it's a conference proceedings in Japan in '93 about circuit design. So it's one of these small, brilliant pieces of work. Okay, but we can kind of explain this very easily. So from time series, you're familiar with the Joule-Walker equations. So it's like a consequence, again, of conditional independence. So again, we start with the way we can simulate from Gauss-Markov field. So if you xi condition on those with a higher index, you have this kind of linear form. So this is the backward solve. This is the same starting point that we had earlier. Now you just multiply by xj and doing the expectations on both sides, as you can do for the normal thing, and you end up with this recursive form for the covariance. So sigma ij, you have an extra term if they are I and j is equal, and then you have this form. And we don't need to sum over all terms. We only need to sum over this term where this matrix element here is non-zero. Okay. So it turned out this define a recursion in the sense that if we have a loop from if we go backwards, and we go in a loop from j from n to I, so we go from the bottom up to the diagonal, then we can compute all the margin variances. Of course, this is nothing new, it's just another way to look at standard things, you know. The point is that, if we go back here, I need to solve these kind of recursion, but I cannot afford to do it in this plain form. So I need to compute all the margin variances. I need an outer loop here, and I need the I in this set, but I don't want to compute from n to I. So if there is a smaller set that I can use, that will simply do that. So it's a smaller set would mean that it's a set of all I and j, so I have all the diagonal terms, but they also satisfy the property that if I in this set, and I have already computed this term. Okay, so if ij in this set and k is in this kind of future of I, where this is non-zero, then this kj is also in this set. So it's simply can I find a smaller set where the recursions are still valid? Okay, so the main thing is that, and this was the kind of result of this 73 paper, is that it turned out if I take the Cholesky triangle, all the terms that I compute in this triangle defines a valid set. So it means that if I'm computed this Cholesky factorization, I can also use exactly the same terms to compute, to invert the matrix. Invert the matrix, I only compute some of the terms diagonal included, and it also would include neighbors. Okay. And this is the proof. It's very, very simple. If you have this property of not being condition independent given the future is exactly what is needed for these recursions. Okay. So it simply means that it's super easy to do in theory to do this kind of part. So the loop is from I is 1, from n to 1, for decreasing j in this set. This set is a set of non-zero values of this factorization. I simply compute the margin variance from this equation that I derived, essentially the Ewell-Walker equations. Okay. And if you have a band matrix, this is exactly what you do for the Kalman smoothing. These are the Kalman smoothing recursions. Okay. So a special case is always the Kalman smoothing recursions. Okay. Okay, so that was all the kind of the background, but you might think is this really needed? It turns out it's desperately needed, and much more than you see here, because we have to kind of redo everything we want to do only using precision matrices, never using covariance matrices. Okay, it's not difficult. It's just a long process you have to go through. So essentially, we're back to we're back to the concept of a latent Gaussian model. We're back to statistics, away from numerics. And we have this very, very simple model. We have some parameters that are non-Gaussian. We have a huge Gaussian vector condition on this parameter, and then we have some data. There is no linear predictor here because we want more generic representation. So only a few of those are observed. And this is the class model we look at, and this is super, super simple. So based on this, we simply want to compute marginal distributions. Okay? So for every value, you want the margin property. You want the mean, the variance, the quantiles, all these kind of things. And we approach this by simply computing marginal distributions. Okay, for all the latent field and for all the hyperparameters. So this is the kind of the task. And yeah, can we do that without MCMC? And the answer is yes. And the point is that you can kind of gain both speed and accuracy. Of course, there will be nothing in this algorithm that say that I can get arbitrary close, as you can do with MCMC. You can always run it to the bitter end and you will know the result. It's asymptotically, it gives you the correct result. But for a given time, this is way, way better. Okay, and this is kind of a little bit the win-win. You can do it faster, but you can also do it more accurate. Okay, and this is almost too good to be true, but there are so many things here that simply play well together. It's just almost like magic, but yeah. I'm just going to go through the calculations in a simple example where you have observations. It's just a smooth function plus noise. So these are the data. I want to smooth the data. And I do it with a proper Bayesian model for this. It's like a simply overkill, but you'll see how this computation can go. So this way it's computed, and we just want to smooth the data, and this is not very difficult. You just draw a line around here and you're done, you know. But now we want to do that kind of properly. So we say that the likelihood is Gaussian and with a fixed precision. If you go back to this case, we'll have dimension of this is just 1, and this is Gaussian, and this is also Gaussian, and then it's no surprise that you can basically do this analytically or numerically. You can do everything you want. Okay. So we have a fixed variance for the noise, and then we have this latent process. This is, just take it as a spline. A spline here is simply that the second derivative is noise. Okay, you see here, this is, think of this as a continuous time process, but we only know it at discrete time points, and this will be the second derivative, and this is the square, so this will be noise, and this is Gaussian, so this will be the square. Okay, so it's like a stochastic spline. And then we have parameter for the smoothing. For simplicity, just think of it, we have some prior, this is a gamma prior. To determine the prior, this is another issue. Okay, this is not a good prior, but it do the job at this point. Okay, so based on this, we want to compute the marginal distribution for theta and for every value of the spline at time points 1 to n. Okay, so we have the smoothing parameter, and for every point here, we want the kind of the mean and the distribution for the spline at this point. So these are the marginal properties we want. Of course, things with a Gaussian likelihood, everything is nice. You can integrate out the Gaussian, and this is simply using this form that the conditional distribution for the smoothing parameter given the data is simply this. You can rewrite it at this. You have the joint distribution and x and the data, and it's a prior, and you divide by the Gaussian conditional distribution. This kind of concept of dividing by the conditional is the same as integrating out. I find it conceptually easier to derive a conditional distribution instead of integrating out something. Okay, what you learn at school. Huh? So this is a joint distribution, and this is, if the joint is Gaussian here, then of course the conditional distribution is also Gaussian. You can compute everything. Okay, no big surprise. So it means that I know exactly this marginal distribution is only the thing that the detail is only proportional to. Okay? So it means that I have to do some kind of exploration. And how can I explore a density if I cannot see it? I can just evaluate it for at a given point. You simply treat these as a optimization problem. The first thing you do is you find the optimum. You maximize this function with respect to theta or log theta. You find the maximum. At the maximum, you do the Hessian, the second derivative, which essentially gives you the scaling. And based on this scaling, you can explore the neighborhood. Explore the neighborhood is like you're going a fraction about the kind of the margin variance you get from exploring the Hessian at the mode. You simply evaluate next step, until the density is small compared to the mode. Okay? So you just go in this direction until there is no mass left. And then you explore the other direction. Then you have computed the margin densities at all these points. So all the ratios are exact. It's only that you don't know the margin, the height. And then you simply can do an interpolation, and based on this you can do the renormalization. Okay? This is not the exact marginal density, but it's the ratio between the 2 points here is exact. And the rest is just interpolation. So this is our kind of computed marginal density. And you see that you can do this automatic. You first find the mode, you kind of compute the curvature at the mode, and based on this you are able to kind of explore what happened in the neighborhood. Based on all these points, you kind of build an interpolator. Based on this interpolator, you can do a renormalization. And based on this interpolator high dimension, you can then compute marginals for this. Okay. So this is essentially what happened. And then we have the marginal distribution for the smoothing parameter. We can compute that directly. And the next thing is that you want to use the same, we'll kind of use this to compute the marginal distribution for the spline. Okay. So we want the spline at a point xi, given y, given the data. And of course, you can condition on the smoothing, and you can weight with this distribution. Okay. And it turns out this one is Gaussian. Of course it is. Okay. So if you know good integration points to do this integral, then you can simply compute this distribution directly and simply weight with the posterior for the smoothing parameter. Okay? And you see here, to do this, we need to compute the marginal distribution for all x's and then kind of compute the diagonal of the inverse to get the marginal variance. So that's why you need the inverse of this sparse matrix. And you see here, so you can do the same thing. So this is the marginal, the posterior for theta. So when I computed here, this point here, I also computed the conditional distribution. So the only thing I need to add is invert that matrix and keep track of the marginal variances. If I do that for every of these points, so the way you do exploring is also the way you're doing the integration. These are all the marginal distributions that are computed. They are not weighted. If I weight them, I get something like this. And then you do the integration. It's simply, for every point here, you sum all the contribution on this side. Okay, and then essentially you get the marginal distribution. So this is how you kind of can compute it directly. So you see, this seems a bit of an overkill in this simple case, but the point is you can use the same idea in more general cases. So it's only this, you have more than one parameter, you have the data are not Gaussian, so we need another trick to deal with this. And is simply get a little bit more complicated. But the basic ideas are still the same. In 2 dimensions, you do this, you're going to explore the mode, you need to compute the Hessian. Then you get new directions that is more independent. You rotate the system to get there because you have more independence. It's easier to explore when you have more independence. You can lay out points. For every one of these, you do this. So in this case, when you don't have Gaussian data, nothing is exact anymore. So you're bound to do these Laplace approximations. So simply, the Laplace approximation is that if x and y jointly is non-Gaussian, the conditional distribution here would in general also be non-Gaussian. This we know. This is unknown. So what you do is that you approximate this guy with a Gaussian approximation. And why the Gaussian approximations would be quite good? Because the whole model setup is that x without data is Gaussian. And with Gaussian data, it's still Gaussian. So with non-Gaussian data, it's close to Gaussian. Okay? And then you build this in and you get even That's why you get, and you have to do the same thing for the next layer. Is just getting complicated, but it's still the same thing. We kind of build up an approximation of the joint, and based on this, we'll derive the marginal distributions. This joint is also used here for the integration. We approximate this, and we approximate these integrals. And this is how it's done. It's not difficult. There is just a lot. Okay, so there is no difficulty. If you do it like this, if you work out the details, it seems like you're using this Laplace approximation that we're going to discuss in cases where it's almost correct. Okay, if we do that directly, if I do this approximation by doing a joint Gaussian approximation to this theta and x, this interaction between theta and x, it doesn't work. This is a bad idea, and this gives horrible results. So you need to kind of do these nested versions. This is one Laplace approximation, and this is another one, and then you do an integration. That works. The other cases don't work. And this is my second favorite slide. So what the key thing in all approximations is that we have a conditional distribution of x given y of this form. We have something Gaussian, and then we have likelihood contribution. Okay. And the question is, how do we approximate this with a Gaussian? Of course, you're doing a Taylor expansion here, and you find the mode, and at the mode, you will have a diagonal term for Q, and you have another mean, which is the new mode. So this is the easiest way to do this approximation. And then you see essentially why this is working and under what conditions this will be a good approximation. So if this is quadratic, essentially if this is Gaussian, you have the Gaussian likelihood. You see, if you do a quadratic expansion of something quadratic, then it's exact, and this is exact. Okay. If this is non-quadratic, the error is in the third order terms and higher, like in the skewness and higher. Okay? So it cannot be that wrong. And if you approximate this condition distribution with the Gaussian, you see that before data, it's already Gaussian. And the way we do statistics is that we introduce smoothing, we introduce borrowing strength, we're introducing smoothness. This is why, we trade in dimension. We have a spline with high dimension, and then we say that this is very smooth, essentially, so it effectively lies in a low dimensional space. So this kind of borrowing strength simply means that this prior here is kind of strong. This is the way we construct it. So essentially, this would overwhelm the likelihood. So the likelihood would mainly change the location and the margin variance, and do much less when it comes to skewness. Okay? The other good thing about this expression is that if you take away the likelihood, this is the prior, and this has some kind of sparsity that's constructed from the model itself. When you condition on the data, you see that the change is only we add something on the diagonal. So the sparsity pattern, the underlying graph is the same. So the computational cost working with no data and with data on these approximations is the same. So the data doesn't destroy the sparsity pattern. Okay? And then you also see what is the influence of the data. In the likelihood, there is no xi, xj. So it means that the dependency structure in this approximation comes only from the prior, from the model. So the data doesn't really do anything, doesn't add anything when it comes to the dependency structure. So all terms here with xi, xj only comes from the prior. Okay? So it also means that the Gaussian approximation would be more accurate. Just a note on the Laplace approximation, you have all seen it, and it's like the classical, the only thing you can kind of do when you have an integral of some form, exponential integral of something exponential, you have n times a function, and then you look at what happened when n increase. Okay, and you can kind of compute the limiting case, and then you can kind of scale back. So what you can do is you can do a second order expansion of this g, assume that it's g at this point is 0. If you are at the mode, then the gradient is 0, you end up with a quadratic term, and then you see that this is something Gaussian-like. So the answer of this integral approximation of this is like the normalizing constant for the normal. Okay? So the square root of is the same thing. And of course, when n is high, you get more and more squeezed, so then it's more and more accurate. The cool stuff is that you get a relative error in this structure. This is the important thing, that the estimate of this integral divided by the true value is like 1 plus order 1 over n. Okay, two things. There is a relative error, so it's not like this MCMC additive error. If you do an expectation using MC, you have the true value plus something, an error that goes like plus an error that goes like 1 over square root of n. Here you have a relative error. You have relative error and you have 1 over n. So it's like square root of n faster and is relative. Okay, this relative is important because the structure of the error will be different. If you have multivariate, of course, you just do the Hessian and then you get the determinant of the Hessian matrix, the square root. So it's the normalizing constant for the multivariate normal and then nothing else change. Okay. The main thing, if we use this kind of idea to approximate the marginal distribution for the hyperparameter, this is the first step in the kind of algorithm. The main result is that if you have repeated measurements and the approximation you have is normalized, it integrates to 1, then within a square root of n neighborhood, you have like an increased accuracy, n to minus 3/2. So it's not 1 over square root of n, additive error, it's a relative error that is 1 over n to 3/2. It's like square root of n cubed. It's an amazing kind of accuracy. Of course, there are assumptions here, and the assumptions made for this doesn't apply to the concept of models that we're using. We don't have replicated data. You don't have 2 parameters and then you have n independent observations of those. If you have new data point, there is usually a new random effect connected to every data point. So essentially, let me see if I can find it. Essentially, what we have for this kind of model is that the dimension of x grows also with n. Okay? So it's not that dimension of x is fixed and your n goes to infinity, but both dimension of x and n go to infinity. And then everything can happen. But still, the basic idea still apply, because this is the way we kind of do our models. We we trade in dimension. We have a model with high dimension, and then we simply reduce it by smoothing or saying that something is equal or close. Okay? So the effective dimension grows much slower than n. Okay? So this kind of effective dimension and smoothing kind of emulates this kind of concept of independent, of replications in the measurement. So the more smoothing you have, the more borrowing strength you have, the better the kind of approximations will be. So you can think the worst case scenario is there is no smoothing, it's just independence. And this case is still a latent Gaussian model, but you need some kind of concept of smoothing to get this kind of going. Yes. We can do other things as well. Model selection, yes. Arke will talk more about model selection, how to do it properly in the Bayesian setting on Friday. The main thing there is Bayes factors. Okay. Bayes factors, or the marginal likelihood, is usually an awkward thing to compute from MCMC. Here it's simple, it's like a byproduct. It's a normalizing constant from the, it's not here. It's a normalizing constant from the theta given y. Okay? So we have internally an approximation to that. We need to kind of normalize it. And that normalizing constant turned out to be the log of that is the marginal likelihood. Okay? So the marginal likelihood is, in this case, is a byproduct of the computations already done. You can do this deviance information criteria, DIC, or better, the WAIC, which is better. You can also do, because it's only depend on the properties of the predicted distribution or the likelihood. So it's the kind of the deviance. So properties of this is only depends on xi, so we only need the marginal distribution for xi and for theta, and you can work it out. So it's like a direct consequence of all these kind of things. You can do cross-validation. If you are in the case where if you remove a data point, it doesn't change the marginal distribution too much. So you cannot really predict what happened. You know, when you have this kind of removing one data point really change things enormously, then you have to recompute it. But in the case where it's fine, you have the marginal distribution for xi, and you can remove a data point, you simply divide by the likelihood. So then xi with that data point removed is simply part of this. If you have like overlapping support, you can just compute this. So you can do this kind of cross-validation things under these assumptions. Yes. So these are essentially the thing. I thought of mentioning a little bit what's going on if we go to more spatial models, because the normal spatial models are non-sparse. Okay, so there's more Gaussian fields with Montern covariance functions, and this is like the building block how to go with models in space and time later. Okay, and there, if you read literature, everything is about covariance functions. You start with covariance function is positive definite function, and I shouldn't say anything because the French school is very strong on positive definite functions. Okay. You have a dense covariance matrix, and everything is fine. Dimension is low. You can do whatever you want. The dimension goes high, you cannot do anything. And to work with covariance function is wonderful because you have all these nice properties. In fact, you know the marginal properties. There is no kind of boundary value issues. You know, there's a lot of good things, but it's kind of resolution consistent. If you know the covariance function, you can put the points anywhere and simply compute the joint distribution. And it's all kind of work out and make sense. The only thing that is not good is that it's horrible to compute with. So it's dense, there is no simplification unless in very simple cases that is easily destroyed by non-Gaussian data. And you end up with n cubed. And to generalize beyond this, what happens if you have non-stationary models, if you have models on the sphere of some other kind of object, what do you do if you have an island, you want to have dependency going around islands, all this kind of, what happens beyond the standard case is, it's super, super difficult. Then you have this kind of, on the other side, what we have discussed here, that the Gauss-Markov random fields, which is a completely different view of the same thing. You can think of the conditional distributions being very, very, conditional distribution only depends on the neighbor, and this defines kind of the graph. It has a very simple conditional interpretations, small memory. We can do this very, very, very quick. It's so amazing, this kind of software they have for these sparse matrices nowadays. It will simply blow your mind how fast these things are. It has a lot of good properties, but the downside, I don't try to kind of hide the downside, is that it's not easy to specify a Gaussian model by specifying it through conditional distribution to get essentially what you want. It's essentially trying to say something about the matrix by specifying the inverse matrix. To going from the one matrix and to the inverse is complicated. And to try to think that we can control this, that you can design a matrix and then know what the inverse of that matrix is this is a challenge. Okay? It has boundary issues. If you have irregular lattices, it's even more difficult to get everything right. It's horrible. And many of the models that have been used in the literature historically, they are not resolution in the consistent. So if you change the outline of the region, you take a region and divide it in two, you simply change the property of the model. Okay. And it turned out to be a connection between this Gaussian field and this Gauss-Markov random fields. And this, as often, this connection, you find it by doing things a little bit more abstract, and then these turn out to be the same thing. So we can work with stochastic differential equation of this type of form, where this exponent is nu, this is a smoothing parameter in the Matern, dimension 1/2, so it's like a Laplace operator. And then you have Gaussian noise, so this is like a continuous formulation. And it turned out that the solution of this differential equation is a Gaussian field with a Matern covariance function. Okay. The nice thing is that if you have this SPD, the exact solution is known, is that it's Gaussian with this Matern covariance function. And it turned out a numerical solution to the same differential equation would be a Gauss-Markov random field. So if you kind of compute the finite element solution of this differential equation, that solution turned out to give a Gauss-Markov random field. So you see that this simply gives a connection. I can think about doing things with this covariance function. But in order to do all the computation with it, I will simply look at the corresponding SPD, and I have a numerical solution of that one that will give something that is super, super sparse. So I can construct this Gauss-Markov random field through this SPD. So it means that this is totally automatic. You can write down essentially an approximation to the inverse of this matrix directly in for any kind of irregular locations. And how is this done? Numerical solution, this is the finite element idea. You build up a solution by small tents, like a linear combination of some basis function, and these basis functions are kind of compact. And it is all about computing the joint distribution for the weights. And you do this, so what you really do, you try to fit, you have a continuous realization on the left, you try to find the best representation on the right that is simply built up by this basis function. And this kind of tent function, this piecewise linear, they are very nice. They work very good. If you do that, you end up constructing a weak solution, so not pointwise, but the integral is satisfied. You can do the math. You end up, you need matrices as the inner product of these basis functions, the inner product of the gradient of the basis functions. If you do that, then for integral values of this smoothing parameter, you can kind of construct the corresponding matrices, and you do a kind of mass, what's called a mass lumping on this diagonal matrix to get it C matrix, to get it in diagonal, and then you have a sparse representation. So this is kind of the main result. And we mean that we can solve this kind of equations for integral values here. For any kappa, this is depending on the range, at any triangulation at no cost. So you can just write down what the element is. So you have a covariance matrix of this type. You can write down explicitly, not the inverse, but a inverse that converges to the same, that has the same kind of limit. Okay. So this means that you can think in terms of covariance functions, and you can do the math by using the inverse. And this is just the beginning. Because it's if you think of this SPD, you can talk about having non-stationary variant, like a range depending on where you are. This will just be this parameter depending on, essentially this parameter depending on location, and the solution is the same. You can take this SPD, you can put it on a sphere, and you can define Matern fields on the sphere. You can put this on the oceans of the sphere, and you can do the same thing. So all this kind of generalization to non-stationarity, to kind of what happened on the sphere, what happened if you have to go around islands, all these kind of hard problems simply become super easy as soon as you formulate them in this framework instead. And the computational cost of doing this is the same as doing a stationary one. Okay? So you have all these kind of difficult extensions now becomes trivial. It's kind of boring, but it's like a beautiful thing. And this kind of new book that is coming, again, there is a free version out there's a GitHub version of the book that is out. This is a book full of examples how you can do it, because it's not a theory book, it's about all the nice things you can do and how to do it in simple examples. This point process model and preferential sampling, how to deal with if you want to say something about fish, you go and fish where there is fish. And you have to adjust for that to get the prediction for the overall. There is a chapter about spatial non-stationarity. There is about extreme value analysis, about space-time models. There's another applications. So you see it's almost 300 pages just doing examples. Okay. If you want to kind of look more into this kind of topic, there are 2 recent review papers. So one is in the I need my glasses, sorry. Yeah, there is one about the InlaPath, the kind of the inference algorithm, why it works, and the basic idea. So essentially what we have discussed here, but going more into the intuition about this, all the applications beyond what's happening. So this is like part one, and there is a recent one from earlier this year about the spatial model, how to deal with these SPD models. Which is like Gaussian field dealing with non-stationarity models on the sphere, how to deal with islands and all these kind of things. So I like, think of it as a review, part one, and part two. This is in a different journal. And they're quite large, and they should kind of give the overall introduction to this. I think that's fine. Thank you so much.